Welcome, viewer, to my channel. I am Michael with Archimede Design. I'm often bringing you Fusion 360 tutorials as well as prototyping tutorials and other related kind of product business startup tutorials. Today we're going to do a Fusion tutorial and we're going to talk about threads. And yes, Fusion has a built-in thread modeler. Sometimes you run into situations where you have a thread that is not actually in Fusion. I've seen this posted on a couple of different forums, and there are some techniques that you can use. So what we're going to do today is we're going to go through a couple exercises with using ISO threads and UTS threads and Acme threads. So yes, both of those are in Fusion, but there are scenarios where maybe they might not have a more non-standard one. So we're going to show you how to build those threads and other methods in which maybe you can use existing models that are out there to cut those threads. So hey, let's get started. All right, so basically there's many more actually, but when it comes to machined threads, there's three most common ones used that are out there. There's the ISO thread standard, and then there's the unified thread standard, and then there's also what we would call the Acme thread standard or trapezoidal standard. So both the unified thread standard and the ISO thread standard are pretty much the same. They just are basically going to be imperial units versus metric units. So I actually have a spreadsheet that will calculate all the different dimensions and things like this. But if you go to Wikipedia, you can look these standards up. So here you see a shot of what the graphic is for the internal threads, external threads, and all the different dimensions and the equations associated with determining those dimensions. What this does is this worksheet will actually, you can choose what thread density you want, if it's coarse, fine, or extra fine, and then pick what dimension you want. It should filter out the ones that aren't in the fine and extra fine, and then it will, once you pick 1/2 inch or 3/4 inch or 5/8 inch, you'll see that these change automatically, and will give you the diameter, the pitch, the height, the what they call DP, which is kind of like the nominal diameter, for the pitch, and then the minimum diameter. Because when these are actually cut, unlike like wood screws, they're actually flat in the edges and internally. So they don't come to a sharp point. However, it does allow you to override D major and pitch with your own custom diameter and own custom pitch. I should have most of them in here. All these are based on these lookups. These are tables that are already in Wikipedia. And then if we go to the ISO thread standard, it's the same. We can do fine and coarse. There are some instances where you might have a 10 that has a 1.25 pitch or a 1.5 pitch, or 1.1 and a 1.25 and things like that. But there could be an M with a 1.5. In fact, I believe I used a M with M10 with a 1.5 on a project with my truck, which isn't in here. So as an example, let's say you have an M10 and it picks 10 and 1 millimeters. But however, if you don't have, let's say you have a 10 and a 1.5 millimeter pitch. I actually have a bolt like that that's on my truck. So how does this spreadsheet work? If you actually just clear out this selection and you put 10 millimeters here and 1.5 millimeters here, it will then go by that and calculate those new heights and various diameters. So it's a nice tool to have. It is also based on ISO lookups. And you'll note that some of these actually have different pitches for the same size diameter. And then there's also an Acme one. Acme is I wouldn't say it's simpler because technically it uses the same math, but the way they represent it on Wikipedia is a little bit different. Basically, there's a nominal diameter and a pitch. We can choose between imperial and metric, and then choose the different lengths, and then it'll calculate the pitch. And in the same fashion, you can delete it and do your own custom thing. Now, there's some nuances that we'll go through in the modeling because, unfortunately, the best tool to use is going to be the coil tool, which we'll talk about. But the coil tool can only be used in 3 shapes: round, triangular, and square. And it doesn't, even though you give like the triangular shape, which you think would be a great shape for this, because if you kind of connected all these, you'd see it's triangle. The ISO thread is triangle based on 60 degrees. So it's a 60, 60, 60, right? So you have 180 degrees. And so the issue with that is that same standard isosceles triangle is what's in Fusion, and you can't change that. So you're kind of stuck with that shape. So when we do Acme threads, it's going to be a little bit different, which we'll talk about here in just a second, of creating your own custom pattern for threads. And that is the case with the trapezoidal Acme type threads. The unfortunate thing is in Acme, it's a 29-degree angle, and you cannot do that in Fusion. That would be a great addition for them, for you to add your own profiles for the coil versus just using theirs. So the alternative is to do 2 steps. We're going to do a coil and then sweep a profile. The negative side of that is that your model gets really large. Sweeping a feature along a coil has a long model size. So if you have a really large, long set of threads, especially Acme threads, which can be longer, it could take a while to compute if your computer is a little slow. So anyway, so these tools are there down below in the description. There will be a link to the files that I use in this tutorial, as well as this spreadsheet. The other thing I want to mention is that I'm actually not going to go through all the drawings and modeling and doing all that. I'm just going to go through my history and show what I did and talk about what I did, and then leave the rest up to you guys. So all right, so with that, let's us go into Fusion. All right, so the first thing we're going to do is there's actually 2 files that I share with you. One is ISO thread one, and one is a UTS thread. They're really the same thing. One of the files is set up in metric, and the other one is set up in imperial units, so that way you don't have to switch back and forth. The way I'm going to go through this, as I said, is I'm just going to go through my history down here. I'm not going to I've already done all the drawing. I'm just going to talk about what it is and how I set it up so you understand that process. And the process for the ISO is going to be different than for the Acme threads or the trapezoidal threads. All right, so threads is a great opportunity to use parameters. And it's also a great opportunity to use equations in those parameters. So the first thing I did is, based on that ISO standard, I defined a bunch of parameters. I defined the diameter major, I defined the pitch, and then I defined the height, dp and dmin, using those equations. And then I specified what my head diameter was going to be, what the length of the actual bolt was going to be, and then what my head height was. And I can also already see that I forgot to change the units to inches within here. So doesn't really matter inches, it'll still do the conversion in millimeters as long as it's specified as millimeters, because I really just edited the last file, so maybe I'll update that. All right, so once those are defined, first thing we're going to do is we're going to define the actual thread feature. So what I did is, I'm going to edit my sketch here. So some really basic things were calculated here. So in this instance, 5 is the nominal diameter. That's the diameter, that is how the threads are measured. And it is to that outer flat edge. The angle of what it's at, 60 degrees. And then we needed to know how far down this tip actually goes down, because again, it doesn't come to a point, it's flat. So then that was defined, and that was actually height divided by 8, which is in that sketch that's in the spreadsheet. We're going to need some other of those dimensions later, because we got to do some combining of things. But so this makes the basic triangular shape that I want to match when I do a coil. Let's finish that. The next thing I defined was the sketch of the head and some other features that I want to make sure I have. So obviously the head diameter, 14 millimeters in this case. But then there were two other things that I defined. One is I defined a 10 millimeter where I'm going to do a cylinder, and that's going to create the body of thread along that outside. So you know where we had that little height over 8, whatever. It's basically going to make sure that this gets cut out and cuts that part out. And then on the inside of this is 8.701. I have that as height, d min minus height over 4. And what that is that's to make sure, if you noticed, on the inside cut of those threads, it's also flat. So it's creating a cylinder along there that can get combined with this. So you kind of see how that goes here in a second. So, but all these equations are in there, so you don't really need to do anything in this sense other than update the parameters. The next thing we're going to do is we're actually going to use the coil function, and we're going to define a coil. So here you can see I've already done that, and looks pretty good. Looks like a good wood screw and ready to go. But as you know, even though we've done this, we are going to have to do some modification to it. And there's a couple other things I want to show you that I had to add to make sure things were correct. But first we'll have to look at how I built this and talk about that a little bit. So a little bit about the coil function. You can basically define a coil using revolution in height, revolution in pitch, height and pitch, or have it follow a specific spiral that you've already defined. The unfortunate thing is that you're limited to circle, square, and these two different reverse and external, internal triangles. So you can't really do your own custom shape here. That can only be done with the sweep function. And I'll show you how we do that when we get into the Acme threads. Because of that, we are limited to a 60-60-60 triangle in this case. So we are going to define the diameter as dp. The length is actually, in this case, height, and not the height that we have in our parameters or in our calculation, but the length of the actual. In this case, this is going to be a bolt, so the length of the bolt from the the length of the bolt depends on how you want to measure that, if it's the length of the threads or the length with the head or not. But this is with the threads minus a little bit. The pitch, and all these numbers, a lot of these numbers we end up getting from that spreadsheet that I showed you. The angle, what the angle does, if you put it in there, it actually makes the spiral just keep growing out at a certain angle. We're not going to be using that. What our shape is, and then do we want that to be on the inside, on the outside, or on the center? And we're picking center in this case. Now there's this new function, so section size. When you're going through this, you might think, oh, since it's an isosceles triangle, you just do pitch. It's not pitch. So you got to do a little have to do a little math here. So I ended up defining a new parameter, which I'll show you in a second, called section size or sec size, and that basically is looking at that cross section. So it's half the triangle. You need to know that height of it. So that's just a tangent function. So I'll show you what that is, and we're going to create a new body. And so what it does, it creates this shape that matches my drawing precisely, which is really great. Let's just go to parameters. So what I ended to do is this new one called section size. So it's pitch divided by 2, because every one of those sides of that triangle is actually equal to the pitch. The pitch is just the distance between the flat side of that whole entire triangle, between peak to peak or trough to trough. So it's half that. Then divided by the tangent angle, which is also divided by 2, because we're only looking at the right triangle half. So that will give us our actual section size of 0.866. So we have to use that value. You also see the angle. Once I defined or measured that angle in my drawing, it had like a D1 whatever dimension name. I changed the name in here to angle, what I wanted it to be, and then I used that in here as a reference. So if your sketches have any of these defined dimensions that you've not named, you can name them here and reuse them in these equations up here. All right, so we have our coil. And the next thing we're going to do is we're going to now make this into more of a solid part. So first thing I do is that interior circle profile, we end up extruding and creating a new body, and it pretty much just creates that body. And you can see by the size that we picked, it flattens that inside trough for us. So we picked the dimensions right and put in the right equations. The next thing we end up doing, outside cut of this feature, flat side. So let me just show you how that looked. Edit feature. So basically what I did is I did the outside diameter one, and I made it as intersect. So anything intersecting with it would be kept. So now we have our beautiful thread shape. And then I'll show you how these parameters change, because I already had chosen some of my dimensions already. So finally I wanted to start defining my my head size. I kind of left this one at 3 millimeters. It would be a little bit bigger for an M10, but so I defined the head, and then I just cleaned it up a little bit by doing some fillets. Oh, and then there is one final I forgot to say. So when we're here, you can see we really have a rough edge right here. We have to clean that up. I didn't find any standards out there how those lead-ins are supposed to be modeled. Acme threads tend to be a lot flatter. Other machine screws tend to be a little pointier, but so what I did is I did a cross section of this, and then I did a 45-45 at I calculated to be D major divided by 3. Could change these so they're not the same on both and flatten it out a little bit. Maybe this other side could be D major divided by 2 or divided by 4. And then we also put it a little bit above length plus pitch. So I brought it up above it a little bit. And then all I did is just have it sweep cut around to give me a nice lead in. All right, so now that we have this, let's use the power of parameters here. So let's do this in real time. We're going to change our values based on a project that I've been working on that uses a 4 millimeter. So 4 millimeters. And so we want to know what the pitch is. So if we actually go into the ISO standard here and pick the M4, we see that it's 0.5 millimeters. So we don't need to worry about any of the other calculations now because those are actually in the parameters and calculated in Fusion in the file that I provided. So this is 0.5. I happen to know that the head diameter on a 4mm is about 7mm, and the length of the bolt, and it's important here just because if you get this file and it's in inches, don't just put 15 or whatever, because it could take a while to calculate. So make sure you put in the millimeter in here if it's in inches there. So this one's 45mm, and I know that my head height is 3mm. And so then there we go. It created me an M4 with a 0.5mm pitch at 45mm in length. I have not in this file defined if you have hex heads in here, or if it's, I haven't designed this to be a button head or anything like that. You could modify this file however you like to include those things. Or better yet, just import the threads from McMaster-Carr, which we're going to do as an example, but we'll get through the Acme one next first. So, all right, let's talk about trapezoidal threads and Acme threads really quick. So, big difference is instead of a isosceles triangle, it is not. It is 29 degrees. And because of that, we can't use, we still use it. We use the coil feature only because I want to get something out of it. You can technically also use spiral if you want, and do it. I do like using the coil feature. We don't have that isosceles triangle, so we got to use our own shape to basically make this. So that's what I did. This is the process I went through. Picked again the size that I wanted, and ended up getting what the pitch size and all those things were. I can change in imperial metric, and the one that you can download is an imperial version. I didn't make a metric one yet. So this is an example of what it looks like. And we'll go through the workflow here. So as before, we will look at the parameters, and they're a little different this time. So we have D nominal, the pitch, the height, which is calculated the same way. In this instance, it's pitch divided by 2, and that divided by the tangent of half the angle. In this case, it's half of 29 degrees. And with these numbers, we get 0.097. Length I have here is 3 inches, and head height of 0.25, and a head diameter of 7/8. Little bit different process flow, other than I did do this sketch just so we could see the difference and why it doesn't work. And calculated the whole entire triangle that would make this up, but we're only interested in the highlighted parts right here. Really is all we're interested in. And then, like before, we have the nominal diameter. Here is the radius. We know that between the middle here is the P over 4, that whole thing is pitch over 2. And then we know that in the middle, the width of this is actually also pitch divided by 2. And just do some other calculations here on both sides, just as references and things of that nature. But the again, this angle 29 was determined, and in the parameters, you can see I renamed it as angle. I do show a head here. We actually don't use that because a lot of Acme and trapezoidal threads are just rods, but you can put a head on it if you want. So we just make it as a rod here. Little bit easier because I only need to define this internal diameter right here, which is equal to the D nominal minus pitch divided by 2. And let's go through our workflow. So the first thing is I define the coil. And in this case, it's not so important what the size is, other than my goal is to get it that height right here to be exactly what I want it to be, so it matches up. So I have this as a reference point. So we're doing height and pitch again. Again, we can reverse direction if we need to. The diameter is D nominal. The pitch is pitch, 0 degrees. My section size is pitch divided by 4. So then I know that way I know what my section size is. And that pitch divided by 4 is that distance. So it's just half of it. So you can see where this ends, like right in the middle, right along here. That's what we want. Create a new body and OK. And this is what we get. We get a coil just like this. What I'm going to end up doing, not just yet though, is I'm going to use that reference line right there and then another surface to help guide a sweep to make this work with that geometry. But before we do that, we're first going to create a portion, and we're not going to combine it. I don't combine it at this time. They're both separate bodies. I do an extrusion to get the internal part of that, and that was just an extrusion off this circle, that profile that we created. That's going to be a tool we use in a little bit. Now I'm creating a new component. I want to keep those separate. I have two different bodies and I have a new component, and I'm going to do a sweep with that component. One thing to note, doing sweeps this way and doing the model this way, it can take a while, and so be patient. It could crash if you get too big of one, so I don't necessarily recommend modeling Acme threads if you can get away from it. But if you had to, or if you had to create your own unique thread profile, this is how you might go about it. But just wanted to make sure you understand that it's possible. So now I've done a sweep of that, and let me just turn these off. I have it by itself yet, and I'm going to show you how we calculated this. Edit feature. So the way I've did this to get it to work right is you want to do path and guide surface. So the profile is the profile of the shape that we wanted. There's two of them in this case. The path of that body 2, which was the coil that met right in the middle of this profile. It was right here. You can kind of see it's light blue right there. The guide surface is the surface of body 5, which is this internal body, and it's this flat surface cylinder going all the way down. And after you pick those values, you'll get three different bodies, two different components. We have their initial coil, the cylinder, and our profile that was made. Yeah, the sweep function. And the next thing is we're going to combine them. So now that I've used that coil, I don't use it, so I just remove it from the model. It's still there, but it's not there. And then I'm going to do is I'm going to combine this being with the component 1 being my active component. I'm going to end up combining body 1 in that component with body 5 as the tool, and I'm going to keep the tool though. So now we have a solid part that has that feature. It looks beautiful actually. And the next thing is we just need to taper the two ends really. So it's very similar to before, where I do a 45, a little smaller maybe, and then I just cut the edge and I do a mirror of that. So you can see I tapered that edge and then did a little bit of filleting. And I create a construction plane and I just mirror that feature on the other side. Let's turn our sketches off. And then here we have a Acme thread rod that's 3 inches long. And just like the one before, we can go into parameters and we can modify them. So let's do this in real time. Just making a change to this. We'll do a simple change. Let's say we're going to go with a 3/4 inch for the diameter. And so by doing that, we know that it's 1/6 is the pitch. Let's go to modify parameters. Change parameters. So we said we're going to do 3/4 of an inch, and this is 1/6 of an inch. Click OK on that. And now we're going to see some things can happen here when we do this, but because it's never exact. So it did the calculation. I have a nice looking thing. Other than, if you look, we didn't quite cut that edge. See, we have those two edges that did not get cut out. So if that happens, we want a better lead in, then we can just go back and edit this sketch, and you can see why that is. There's a part here. It needs to be able to cut at least all the way down to this point. And so just by changing this equation here a little bit to just make sure we get a good amount. That one goes to the corner, and this one goes to a corner. So there, now we just redefine that pretty quickly and pretty easily. Like, as I said, these files are down below in a link to Google Drive, where you can download these files and that Excel file. The next thing, though, is, all right, what's another way to go about this? Now, oftentimes it's going to be the case where you don't necessarily want to model a bolt, but you need the thread pattern, and you can't find that thread pattern, so you need the hole. So we're going to do a case where we can do a hole here. And let's just do some examples. Just going to do this quickly. All right, obviously we can create holes just by clicking on points. I mean, here we all know that we can just create threads by clicking on a circular feature. We can pick the threads that we want, whether it's going to be standard, ANSI, or ISO. So ANSI unified screw threads is what our spreadsheet is. You can pick that, and then it'll just define it, but it won't model it. You can just model it by clicking on model, then it will physically model it. And then you can pick your sizes. It will automatically pick the size based on your hole, but if you have a small hole, you can make it oversized, and it only gives you choices kind of based on the size of that hole, and the different classes you want. So these are all nice things, whether it's right-handed or left-handed, things of that nature. So that's one way to do that, obviously. But again, if it doesn't have the exact one that you're looking for, then you might have to model them like I showed you, and then use that model to then as a tool to cut that hole out. Another option is to go look for that actual model in McMaster-Carr. And let's have some fun. Fast travel ultra precision lead screws and nuts. Like, that's crazy, right? So this is a very unique thread. I don't even know what the standard is, but I want to use it. So we can actually download the step file with threads. All right, so I've imported this, and it's actually really long. I should have looked at the size that I was picking, but okay. So what we've done is we've imported this thread. You can see it's it looks like it is kind of an Acme thread, but it has really rounded corners. And what we're going to do is we're just going to modify, cut, target body, select tool body. keep the tools. Okay, let's just do an inspection, section analysis, if I can get it. And here you can see it actually cut out those threads into your model. So that's another way about getting, especially internal threads, with a part that maybe that Fusion can't do, but you can find like on the master car and get the solid model of. I've used this a lot where if I was designing a fixture or something that was going to have threads from a pipe or something put into it, I don't necessarily know what the thread definition is on those pipes other than the diameter and how it was cut because it's not defined, but I have the model. I can cut them out using that actual model then to get those threads. That's the end of this tutorial, so hopefully you learned a little bit about using the coil feature, using the sweep feature, importing things from a master car, using parameters and equations in parameters, as well as making your own custom threads and those standards behind it, and also obtaining a few tools that you can use on your own and make some modifications. So now that you kind of know that, you can play around also with your own custom profiles or your own custom threads as well. So please, if you have a chance, subscribe to my channel so you can get some updates on any new videos and content that I put out. Hit the like button, much appreciated, and thank you very much.